Hello?
Can you hear me?
Yes. Am I loud enough?
Yeah, now I can hear you.
Okay. Great.
Excellent.
Yeah, it was mad at me. It was telling me I wasn't loud enough.
Oh.
But yeah.
It's
Okay. Good.
just fine. Um, so, are you familiar with the platform? You know how it works and everything?
Yes, I've done one of these before, so this will be my second one. So.
Okay. Well, I hope this one goes as well or better than the last one.
Okay. Excellent.
Okay. So I see you've already picked C++. Bold move. I like it. Um, let's. So I'm just going to dive right in with a technical question in case you have any other questions.
No, go right ahead.
Okay. So this is going to be kind of an algorithms thing, kind of yeah, it's mostly just an algorithms thing. The idea is you're kind of writing an AI sort of for a some kind of 2D map sort of game where you have a grid and you I'm just going to sort of draw out the grid here. And it's annoying because it keeps putting these like dots in, which it kind of didn't do, but so you're gonna have this 2D grid that you can sort of conceptualize, and you're gonna have your position somewhere on that grid. And let's just say there's going to be these coins are going to be kind of strewn about in the space, and you're going to want to basically collect these coins is sort of what you're doing. So you're just moving around on this grid and you're finding these coins. So let's start just with something pretty basic, and let's just say given the positions of all of the coins in the grid and your own position, find an algorithm that will find the closest one. And let's just say for purposes of for this exercise, let's just use the Manhattan distance. Let's just say you can only go up, left, down, and right. So for example, the distance from, so you're at, once you're like X and Y, you'll say like 2, 1, 2, the coin that's down at like 1, 3. We'll just call that, the distance is 3, which is 1 left and 2 down. That makes sense.
So essentially, the distance is just the difference between, like, if I'm X0, Y0, and a coin is Y1, X1, Y1, then it's just like X0 minus X1 plus Y0 minus Y1, something like that.
Yep, exactly.
Okay. And so you're telling me that I know the location of all of the coins. I have, an array of their locations, say, something like that.
Yeah, let's define a couple classes here to help this along. So we'll just call a class point, which will have int x and y. And let's say that that what you're trying to do is you're trying to return the point, closest coin, given your position, and a vector point, which is the coin positions. So you're going to return the position of the coin that is closest to you.
Okay. And am I just, I guess I'm assuming I have some sort of constructor for point.
Right. Yeah. Yeah. Or you can write one, however you want.
Okay. So let me see. So my input is, I get the vector coin positions. Okay, so yeah, so I get my position and a vector of their positions, and I just need to basically return the coin that is closest to me. Volt. Actually, they're public, so I could just say volt. I could just put those down at the bottom once I figured it out. Result.x. Okay, and then I would just return results at the end. Okay, so in terms of developing this algorithm, two things initially come into my mind. Obviously, the simplest solution is probably just to do the algebra for each point, and keep sort of a running distance. So currently the closest one is 7. I'll calculate the distance to the next one. Oh, it's 6, so I'll replace it, or oh, it's 9, so I won't. And then probably along with that shortest distance, I'd keep a running index, like the shortest one is the third index in the vector currently. At the end, I'd just grab the values from the third one in that vector, and then I would return that. The other thought, which maybe is sort of overkill, I mean, you could do a breadth first search, and that would, I think, also return the value of the closest coin. But that seems, given that we already know the locations of the coins, that would probably not need to be that complicated about it.
Okay. Well, yeah. Let's try the simple one, just so we on the same page.
Okay. So for point key in coin positions, so I'm just going to iterate. I have to change this to a for loop with an I if I need the. I probably will, because I'll need to change it to if the index. I'm going to say that point. Yeah, probably point current. Actually, no, let's use P. Let's do integer x distance, integer y distance, and the x distance is going to be equal to your position dot x minus t dot x, and then y distance is equal to your position dot y minus t dot y, and then total distance is equal to x distance plus y distance. I think that's pretty much the algorithm that we talked about in terms of calculating the distance. And then we're going, now that we've got the total distance, we'll start out with trying to think about if I wanted to subtraction the other way. So for example, in the case of, let's take an example of like I'm at 1, 1, and the other one's at 3, 3. That would give us a negative number for each of them, and we don't want a negative distance. But of course, it could be the other way, right? It could be 3, 3, 1, 1, and then if I did it the other way. So I think I'm going to take the absolute value of each of these, because that way I get the actual the difference between them, and it's always going to be a positive number. And once they've been absolute valued, I don't need to do it for that one. And then I'm going to define up here integer current shortest. I'll just say integer shortest path. That'll indicate this will be a length, so that'll be that. And then integer shortest. Can you hear me? I'm getting some.
Oh, sorry.
Integer shortest index is equal to -1 at the moment. Just because I don't have one. And I'm going to have to change this to a, so I'm going to need that index to get it out. So I'll do change this 0. Coin position size. I don't have to make this an unsigned int, because otherwise the compiler would complain about that, because size returns an unsigned int. I++, and then the first thing I'll do is I'll grab that point p. I think I used a lowercase letter, right? I think I used a lowercase letter. Point p equals coin positions of p of I, rather. I've got that, and I'll say now I can determine if I want to use this distance if total distance is less than. Oh, that's a problem. Shortest path should not start out at 0. I'll have it start out at -1 to indicate that we do not have the shortest total distance equals -1 or if or total distance path
Right. Okay.
and then I will say that shortest path equals shortest path is equal to total distance and shortest index is equal to I. Make sure I'm not, so shortest path was my overall shortest path, and total distance is the one that I calculated here. So shortest path becomes total distance if total distance is shorter than the current shortest path, or if the shortest path is uninitialized. So that seems like that would work. And then let me see if I got I think I might have. We missed a bracket there, so I'll get that bracket there. So these brackets match up, and those brackets match up. And then after I've gone through all the points, I should have the shortest distance. So then, mind, because that doesn't end until down there. Then and I would actually want to declare shortest distance. These two, I think these are the two. Those need to be outside of the for loop, or they would go out of scope, which would be silly, so I wouldn't be able to use them later, which would be bad. And then, that connects to that. And once I've gotten out of this, shortest index is really the thing that I care about. Result.y equals coin positions of shortest index and y. I guess I gotta make this. This is fine. I mean, the x-axes are all constant time. Shortest index x, and then I just return result. I think that should work, because I could try and try an example. So for example, in this case, with I'm at 1-1 and coin at, let's say, 3-3 and 5-5. Well, I'd go through and I'd first have a coin at 3-3. And so I'd calculate the x distance would be my position 1-1.x, which is 1 minus 3, so I'd get -2, so I'd have an x distance of 2. Y distance would be my position, so it'd be 1 minus 3 again. I'd get a absolute value would be 2. So the total distance would be 4. And then I'd see shortest path is -1, so that would get set. And then I'd go through, and the 5, 5 would yield a value of 8, which would be greater than the total distance. And so that would yield that wouldn't change it, and it should go down here, and then it should do that. Yeah. Yep. So that should work.
Looks good. I'm just going to create a little I'm going to take that example that you gave, and I'm going to, was it 3, 3, and 5, 5?
3, 3, and 5, 5 were in there. Yep.
And let's see whether this can actually run.
Okay.
And then I'll say result is, what do we call it? Closest coin.
Sure.
And I'll make this one. So you're at 1, 1.
I'm at 1, 1. Yep.
And then we'll put coin positions. And then we will see out result dot x.
I think we might need another. That's point.
All right. Let's see how this works. I don't think we need that anymore.
Do we not need that any? Don't we need a semicolon after the class, or whatever this thing is?
Oh, sorry. Yes, you do need a semicolon after the class.
Okay.
All right.
Okay. You want to go ahead and run it and see what happens?
Do we need a semicolon after this one too? Maybe, I don't know.
I don't think you need it after main. I think it's just classes.
Oh no, I mean this constructor here.
Oh,
maybe.
So actually, this method point closest coin is not. I guess it's not in the class. I'm not sure if that's. I think it has to be in the class, doesn't it? Or
no, I don't think so. Does it?
I'm used. Well, this is kind of weird because I'm used to you stick the definitions in the .h file, and then this would be
right.
the .cpp file. So I'm not entirely sure what the rules are if you stick it all in the same file. But anyways, you can just run it.
Well, let's see what happens. Oof! Ouch. Okay. Well.
Missing terminating character.
Oh, well, that's just for this. That was
okay.
that line. That's easy.
No, it's still upset.
Oh, this is a pointer. That was my error. Global scope, vector is not declared, so we need to add a vector. All right.
There's probably some, I think I does not name something, so there's some, where's I?
Yeah, okay, let's see. Whoa, what just happened? Suggested alternatives. Vector was not declared. It totally was declared. I just declared it.
I think you have to reset run.
So much
you had to reset it. Point was not declared in this scope. Point result.
It was not declared.
Oh, that has to be capitalized. That's the issue there. Error. Coin position was not declared in this scope. It's probably the same sort of coin position. Oh, I put an S on it. Should be just that should be the same.
Oh no, it's misspelled. Yeah.
I misspell it.
Right here, position in 25. Oh wait, 19 is what we're talking about? No. No, in yeah. So 23. This is misspelled.
Oh.
Yeah.
This is the issue. Points.
Yeah, and I think also for these ones. Yeah, here's where autocomplete really helps. They should get that for CoderPad. That'd be cool.
have to hit the reset button and then hit run.
Yeah, there's still
No
a couple
matching
of position
point.
is still misspelled in like your position and there's an extra S in 25
Which
and
line?
26.
Your position dot x minus your position
Right. It's position without the
POSITION, right?
Yeah. So there was an extra S in there, but I got rid of it.
Okay, great.
No matching function. Oh, yeah, you have to give. Oh, geez. All right. Wow. Thank you, C++. All right, we'll just do this then. Complaining that there's no zero argument constructor.
Yeah.
0 and y equals 0. All right.
Fine.
That's fine.
Okay, and then the last thing it's mad about is error coin positions. I probably misspelled it again. Coin positions.
Yeah, I think it was just a copy paste. That extra S.
Paste.
Yeah. And I think also shortest index. Oh, that's actually how it was spelled before. Short test index. That's fine.
Reset. So it returned 3.3, but this is suggest parentheses around comparison, so it just wants.
It's just a warning. That's not a big deal. Okay.
Yeah.
All right, 3.3. There we go.
Okay.
Now, so, and one other little thing. It's actually, I think it totally works in this case, but the single vertical bar here is actually a bitwise OR. And so what it's going to do is it's going to take the left side as an integer and the right side as an integer and do a bitwise OR of those two integers.
Oh.
And that's fine. In this case, it actually works, but it kind of is taking advantage of the fact that a Boolean gets turned into a 0. But anyway, so yeah, okay, looks good.
And so I'm not totally aware. Maybe you could, if like in Java, the double or the double signal that's a logical OR. Is that also a logical OR in C++?
Correct.
Okay, so if I want to do a logical OR, I do that, and okay, that's good then. Okay. Yeah, that seems to work. Do you want to write some other test cases or?
Oh no, I think we're good for that one. So now we're gonna crank this up a notch. So first question is, what's the runtime of this algorithm?
Okay. Well, it's going to be proportional in part to the number of coins, obviously, because it has to iterate through every single coin. So initially, let's call the number of coins n. There are n coins. And then it's going to have something also to do, I guess it doesn't really matter where they are on the board because I already know their locations. And regardless, I mean, unless there's as long as they fit within an integer in terms of that, there's a constant amount of time it takes to run the calculations. Because it's just distance minus just these couple of lines of code here. So that's going to be constant time. So I guess this algorithm would run in, O of n time, where n equals the number of coins on the board.
Okay, excellent. So let's say that this is a very large board with a lot of coins on it. Is this going to be a good algorithm for finding that? For finding the closest one?
No, because you're iterating through every single coin. My initial thought is that if I've got some massive board, I would want to maybe cut out a subboard like a smaller board, maybe a 10 by 10 board to start, and see if there is see if there's anything within that board. Also, I think breadth first search would look more and more favorable as the board got bigger and bigger, because it's just going to it's going to start at X, and it's going to look at the squares that are adjacent to X, and then the squares that are adjacent to those squares, and it'll stop as soon as it finds a square. So it's going to stop and only hit one coin, and if there's a coin relatively nearby, that could be a lot faster than computing the distance between it and a million coins or something.
Right. Okay. Sounds good. So let's say, just kind of diving into this sort of trade-off a little bit. Let's say that it's a really large board, but there's very few coins on it.
Mm-hmm.
So you've mentioned two algorithms already. One that's the search, where you just sort of look around, like in a sort of physical way, you're looking around.
Mm-hmm.
And then there's the algorithm that you implemented. So which one of those is going to be better in the case that you have a really large board with very few coins in it?
Okay, what do I know about the positions of the coins? Do I have any idea where they're located relative to me, or?
No, you just know it's a big board, and there's a few coins.
Okay, well, I'm going to assume that the coins are maybe on average like halfway across the board away from me, something like that. Especially maybe a little bit farther because there's so few of them. Mm-hmm. And so I'm going to have to go a long way, and the cost of breadth first search expands outwards. Like if I was in the middle here on this square, I would have to do all the squares around me, and it expands corresponding to the amount of area that it's covering. So mm-hmm. in that case, I would imagine that the coin algorithm would be better, because you said there aren't very many coins, but even if the board were full of coins, like every single square was a coin, mm-hmm. then that algorithm would take, let's say the board is n by n, it would take n squared time, because it runs proportional to the number of coins, and there would be n squared coins. Right. But that's not the situation. There's massively less than n squared coins. There's a few coins. There might still be a million of them, but there's a million of them, and there's 10 billion squares in the grid or something. Right. And the breadth first search is going to take, something proportional to 10 billion to find the coin. Maybe it has to search half the board around me. Maybe it takes it 5 billion. So the coin algorithm, I think, would be better in that case. The one I already have would be better.
The first one. Okay. Mm-hmm. So, and so now, and you've touched upon a very interesting point, that like there are cases where it's neither good, it's not good for either one. There's still a lot of work that has to be done. You talked about this one that's like a million by a million wide, and there's a million coins on it. There's no easy way to find it, but one of them is clearly going to be better than the other. Mm-hmm. So let's just say that all you get is the positions of these coins, mm-hmm. and you don't know how big. I guess we'll say and you know how big the grid is. Mm-hmm. How would you choose dynamically which one of those algorithms to choose? So let's say that you basically had you're told that you want to find the closest coin, and you're given this information of the size of the grid and the positions of the coins. Mm-hmm. But it's a general problem, and sometimes you're going to get a grid that has tons of coins on it. They're very mm-hmm. densely packed, and sometimes you're not. Mm-hmm. And you're going to have to find some way to choose between the two algorithms.
Okay, so I know the size of the grid, and I know the number of coins and their positions.
Yep.
Well, it sounds like this is kind of like in a hash table. When the hash table gets too full, it stops working properly because it gets like, you get too many collisions.
Right.
It sounds like I want to develop a ratio between basically a density factor. And this density factor should represent, say, the number of coins per grid square. So something like coins divided by number of cells, or number of cells. And beyond a certain point, if it's really dense, then I would want to use the breadth first search because there's probably one close by, and correspondingly, because it's so dense, there's a lot of coins. But if it's very sparse and there aren't very many coins relative to the number of cells, then I would want to use this algorithm that I wrote out.
Okay, that sounds very reasonable. Now, so let's dig into this ratio just a little bit. So it's the number of coins over the number of cells, and you will define some kind of arbitrary constant that will be over or under in terms of your density to pick one or the other.
I don't think it should be arbitrary.
Well, I guess you would have to find that somehow. And I haven't really given you much way to pick that number. But one question I have is it that you're going to want some like, oh wait, where did I just hit enter in the wrong place. Are you going to want to have it so that, if, density less than, this lambda, which is, so where density, like I'm saying, is defined like that, is less than some lambda, then you do algorithm 1 else algorithm 2. So this is one way to do it, but is this the formula that you're going to want?
Density is okay.
It's kind of a. I guess what I'm asking, the question is, this is setting up a linear function where there's this linear relationship between the lambda and the density, and where and at what point you have this flip. And the question is, do you want that to be
I think I see what you're saying. So as the grid gets bigger, tell me if this isn't where you're going with this. As the grid gets bigger, the depth first search is going to perform poorly, not regardless of how dense the grid is. Obviously, if every single square is filled with coins, then no matter what the size of it is, the depth first search is O of 1. But generally, as you have a higher density level, there's still going to be more space. My intuition is that, let's say we take two cases, one where there's 1,000 squares, A, and then one where there's 1,000,000 squares. And let's say in both of them, the coins to cells ratio is, say, 1 over 4 or something. So there's one coin for every 4 cells. Now, if we assume that, if we assume the cells are sort of the coins are randomly distributed, can I assume that they're not sort of clumped up or anything like that? Then, regardless of how large the overall grid is, there should be a coin about every 4 cells, which means that my depth first search should have the same running time regardless of how many cells there are. I guess the difference is that the running time of my default algorithm in this case would be much worse, because this is going to mean that there are 250,000 coins, whereas this means that there are only 250 coins. So while the depth first search should, on average, have about the same performance, because it's going to have to go, say, about 4 cells, the cost in the naive algorithm, let's call it, gets much larger. So we'd want to include a factor here that represents the fact that the naive algorithm gets more expensive regardless of what this ratio is.
Okay, very good. And what's the proportion here? So, you know, as the size of this grid increases and this density factor stays the same, how does the size of the naive algorithm grow versus how does the size of the depth first search, or the search, grow?
I'm going to change this. I want to change C to be the number of coins on the board, so that's O of C. And then I'm going to say that N equals the total number of cells. So it's not the length. Oftentimes they say it's N squared. It's just like the length of a row by the length of a column. It's going to say N equals total number of cells. And I think from this example, we can tell that as I increase the number of cells 1,000-fold, from 1,000 to 1,000,000, that also increased the total number of coins by a factor of 1,000. And so it looks like the factor, the increased cost of the naive algorithm is proportional to the total number of cells. So if we increase the board 1,000-fold, it increases the cost of the naive algorithm 1,000-fold, given the same density. So, yes. So in terms, go ahead.
Oh yeah, so okay, so that's excellent intuition. And now you know, I think you've convinced yourself that just looking at that lambda is not necessarily going to give you the right choice, because it doesn't work. It works well for some sizes of the boards, but not others. So how are you going to
integrate it into the equation?
To adjust that,
Okay. So I've got the density is less than lambda. Let's say lambda is something like, I mean, it could be 0.8 or something, whatever it happens to be.
Whatever.
Lambda equals 0.8. And then, well, I want to think about the sort of the absolute cost of the, I know the absolute cost of the naive algorithm. I want to figure out the absolute cost for a given size of the breadth first search algorithm. So if I have 1,000 squares and we're dealing with the 1/4, then the cost of the breadth first search is going to be 4, and that was also true with the 1,000,000 squares. It's also going to be 4. My initial reaction to this is that it seems like in most cases the breadth first search is going to end up being better, but in terms of determining it,
well, if there's 1,000,000 squares and there's 3 coins, that's not really going to. There's definitely, the other algorithm is certainly better in that case.
Yes.
So there is a cutoff.
That's true. I guess I'm looking at values like 1/4 or 1/8 or 1/10.
You're certainly right that as that coins per cells number stays the same, that much more often, and as the board grows, it certainly becomes more and more likely that the search algorithm is going to be better. But there definitely is a cutoff.
So if my density is 1/4, density times n is the total cost of naive, right? Naive density times n, because whereas the cost of BFS, best first search, equals squares. The cost of BFS is just I feel like it's just the inverse maybe of the inverse of the density. So like if it's 1/4, yeah, it should just be the inverse of the density.
Yeah.
Of density. That's not a real function, but anyways. Yeah, I'm sure I could like figure it out. It's super important. So if density times n is less than the inverse of the density, then I would choose that. So let's double check this. So for example, so for example, there's 1,000,003 coins, then the inverse of the density is going to be a million. It's going to be some tiny little thing. Yeah, I think that'll work. I think that's right.
Yeah. There you go. No, that's really good. There's only one tiny just piece there that so you have density times n is less than the 1 over the density. Can you rewrite that so it looks a little bit easier on the?
I guess, yeah. I mean, it could just be 1 over. You could just say 1 over. Oh, you mean you just want me to write it as 1 over the density, or do you want me to write it?
Okay. So that's definitely right. So so is there a little bit of algebra we can do here to make that a little bit? I mean, this is a very minor point, but
yes.
So look at how density is defined.
That's going to be, we'll call it C divided by n. C divided by n is this thing. And I suppose I could also make sure the n's are the same. There's if I multiplied both sides by n, then this n would cancel. No, sorry. It's 1 divided by c over n, which is the same as n divided by c, I believe.
Yep. And then what's this density here?
And this has an n, and this density is also coins. Is it just do insert? I'm doing insert. That's not good.
Oh.
C. This is also c divided by n. So those n's actually, c divided by n times n, those n's cancel. This is just c is less than n over c, I guess.
One other simplification you can make to there.
I mean, I could multiply both sides by c and say c squared is less than n. Yeah.
Perfect. Yeah. And so you can see here that you've essentially got the runtime of your algorithms on the two sides. So the runtime of your naive algorithm was O of n, and the runtime of your other algorithms on the other side. So that's
the number of coins.
Number of cells.
Number. No, I think C was the number of coins on the board, and N was the number of cells. What happened? Did we do something?
Ooh.
So.
Right. Yes. Okay.
N is the total number of cells, and that's the. N is the total number of cells. C is the total number of coins. Yes.
Coins.
Or did I change these and maybe not change it here? This is
No,
points divided by cells.
Oh, I think actually I think it did. See, yeah. Oops, we lost our work. I think it actually is. It's the other way around.
It's end of.
Yeah, because here they're called. They're both with C.
Okay.
Yeah. Anyway, awesome. Very good. Now, one more piece that I'm going to throw in here as this is going to be, again, not so much about the coding, but about the methodology. So let's say that it's not just you who is on this board. You have some competitors. And your competitors are also going after those same coins. And if they go towards a coin and they get there, everyone moves at the same speed. And if they get there faster than you, then they take the coin and you don't get anything. So
am I wanting to try to go to coin? So there could be a lot of coins on this board. Are there a lot of opponents, or is there just one opponent?
There's well, I mean, in the most general sense, there could be any number, but any number of each. But as we've seen, the relative number and the relative size do play a big role in which kind of algorithm you want to use. But let's just, for sake of discussion to get started, let's just say it's a board that's this size that we have down at the bottom, and that there's a small handful of opponents that are also competing with you for the coins.
Okay. Well, I initially think I still don't want to go from coins that are far away from me, right?
Right.
So I think I might want to. I could essentially sort my list of coins by their distance from me, and then I could go through and calculate how close each of the coins is to an opponent. And it gets complicated because you might want to think about the fact that if there's a coin that's really close to an opponent but is relatively far away from me and isn't the closest coin to me, then he might go for that coin, and then I could go to a coin that was closer to him because I know he's not going to go, maybe there's this coin that I want to go for is 10 squares away from him, and it's 15 squares away from me, but there's a coin that's only 5 squares away from him in the other direction, so he's probably going to go for that coin, so I can still go for the coin that he would otherwise get. So that's one thing that would make it complicated. But in terms of a simple first pass, I think I would just calculate the coins, get the coins that are closest to me, and sort my coins via how close they are to me, and then I would look at them and see how close each of them is to an opponent, and maybe provide an equal weighting of. I could do two things. One is I could provide an equal weighting of the distance from me to the coin and the distance from an opponent to a coin. Alternatively, I could eliminate any coin that was closer to an opponent than it is to me. So, because assuming that they might go for it and get it before I would. So, if the distance from the coin is, say, 3 from me, and it's only 2 from the opponent, I'll eliminate that coin, assuming they're going to get it, and I'll find essentially the shortest path to a coin where I'm closer to it than an enemy.
Okay, it's an excellent start. Now, let me see. All right. So, let's see if we can. So you have So you have this set up here. I'm trying to think if this brings out. So you said that you're going to eliminate any coin that's closer to an opponent than it is to you.
That was my initial thought. Yeah, but I see with
So
this setup you're creating.
look at this coin. So in this world, you get just this coin on line 87 here. That's what you get because the other people are closer to all of the other coins.
Can they only go for one coin and then they're sort of sated or something? Or
let's just think about it in terms of like a single one.
a single one.
That everyone gets a coin and then you move on to the next map or whatever it is, just to simplify it. So in this case, actually, this coin over here is closer to is every coin is closer to an opponent than it is to you. So you don't sort of win outright any of them. But in terms of this sort of sating, as you said, they're sated by the two coins that are the closest to them, and that leaves this one down in the corner open to you, because they're not interested anymore.
Okay. Well, I guess what I could do is I could calculate. This is going to sound really computationally intensive, but I could calculate the closest coin to each opponent and assume that they're going to go for that one. Yeah. And then I could eliminate that coin from my list. And then I could just, of the coins that are left, choose the one that's closest to me. Now, the one modification that immediately pops to my mind is when I calculate the coin that's closest to them, I could check and see if I'm closer to it, because then I could just get it away from them before they could get it. But other than that, yeah, I think I would just calculate the coin that's closer to each opponent, and assuming I'm not closer to that coin than they are, then I would just eliminate all those coins, and then I would choose the coin that's closest to me of what's left.
Okay. So I see that. But what about this one? So I'm going to move this guy down one just to make the math a little easier. So you said you pick the coin that's closest to each opponent, and then you eliminate it from what you have access to. And I think actually to make the math work out, I need to do a couple more little things, but you kind of get the idea. So from that algorithm, this coin is the closest to opponent number one, but this is also closest to opponent number two here. So you would only end up eliminating this one coin from your search.
It's an iterative process, so I would iterate through each of the opponents. Through each of them, I could calculate the currently closest coin to that one, and then eliminate it. So then I'd eliminate. So I'd do this guy. I'd calculate the closest coin to him, and then I would eliminate it. And I mean, yeah, so that would be gone. And then I'd do this guy. I've already eliminated that coin from my list or my data structure. So then I would calculate the closest coin to him, given which coins are left. Now, obviously, if I wanted to make this like really, I guess, comprehensive, I could try and figure out if, say, let's say this coin, there's a situation where I calculate this guy, and I think he's going to go for this coin that it's closest, but actually there's another person who's closer.
Right. So I was going to say that, like, what order are you, like, that would work if you are sort of traversing this in this ideal order. But if you had accidentally picked this guy first, you would have said, oh, his closest coin is this one over here. And then actually that's not that wouldn't have been the correct choice, because another opponent who you would have seen later was actually closer.
Yes. So, I mean, this is going to really hurt the running time, but what you could do is you could calculate, I mean, so you go to a particular coin, or you go for a particular opponent, you find the closest coin to them, you then have to check all other opponents, and see if any of them are closer. If none of them are closer, then you would say this guy goes for that coin and gets it. Otherwise, you would take the other person who's closer and say no, they go for the coin and get it.
But that still
right
isn't
through.
quite right. So you're getting closer, but okay. So let's just do this here, and we're going to. It's sometimes a little bit hard to come up with the exact answers here, but okay. So we have, for example, here we go. So let's say we have this setup. You start with this opponent.
Oh, I see what you're.
Closest coin, and yet you're going to give that coin to him, even though actually he wasn't interested in your coin, even though he's closer to yours. He's still not interested in it because he has one even closer than that.
Okay. I think I need to for each player, calculate the closest coins to them, and then I need to iterate through the players and check if there is a player who is closer to my desired coin, and is that coin their closest coin. So, and then, so for example, let's say I'm starting on Y, or I could even just do it on myself, right? So I've calculated out the closest coins to everybody. I say, here's this coin. Which one on this map would be closest to me? Like this one over here, probably, I think. 1, 2, 3, 4. Yeah, these two are equally. Well, let's say this one was farther away or something. This one was So I'd start with this coin because it's closest to me, and I'd say there is a player who's closer, and it is his closest coin. Because it's his closest coin, because he's closer, and to be really sure, I'd have to check that no one else was closer than him. So I'd have to check that all the other ones weren't closer. Right. Then I would say he's going to eat this coin, so I can't go for that one. So I don't know. Right. So then I have to get my next closest coin, and this is like 5, and these are about, I don't know. I'm going to move this one again, so it's like farther away. And then I'd go say this one's the next closest one. Y has been removed because he's sated, as we said.
Right.
And then I would say, oh, but this one, this coin is Y's closest coin, and he's closer than me. So because it's Y's closest coin, we know he's not going to go for another coin. He's going to try and go for this one, and he's closer than me, so he's going to win. So I can't get that one either.
Yeah.
And then, are you still there? It said you disconnected.
Yeah. No, I'm here. Yeah.
And then these two are sated, so I'd like to put an S next to them or something like that. And so then I would say, well, the next closest coin for me is this one. And by now I've eliminated all the other players, so I wouldn't find another player that was closer than me. And so I know that I'd be able to get it, so I'd go for that one.
Okay. Yeah, no, that's good. I think that I think that will work. I think the sort of typical way you would do this is so, and you're really close to this. You said for each player, calculate the closest coin to them,
Mm-hmm.
and then you sort by their distances. And so you
Mm-hmm.
know that the person who has the shortest distance to
Mm-hmm.
their desired coin will
Mm-hmm.
automatically get their coin. And that's actually the only greedy thing that you can say at that point is that given that group of people and the
Mm-hmm.
coins, the opponent or the person, whether it could be you or it could be one of the opponents, the person who's closest to their coin is going to get it. And there's
Mm-hmm.
kind of nothing else you can say at that point because there's all these weird corner cases and all this blah blah blah. So then you remove the player, you remove the coin, and then you have to repeat the whole thing over again. You have
Mm-hmm.
to find their closest coin again. Now that there's like one less coin and one less person, and
Mm-hmm.
then you keep going down until you are the person who's the closest to your closest coin.
And that has a lot better running time than what I proposed because if I'm checking if there's a player who's closer to my desired coin, this whole step down here is going to take a lot more time than probably just getting the group of people for a given coin and eliminating the person who's closest. Or as I take a coin, each player. I guess I have to calculate the closest coin to each player, and then, yeah, that makes sense.
Yeah, and it's not there. There's no sort of quick and easy way to do it. There's sort of all computationally. If you want the true and correct optimal answer, it's just you can't get around the computational complexity. But
Mm-hmm.
uh, but yeah.
Yeah.
Okay, nice, awesome. That was it. That's all I got. Did you have any questions for me or any thoughts before we take off? I'll put some notes in the platform later. But did you have anything before I go?
Yeah. No, I mean it seemed like a good question. I like the little grid that you drew, and yeah, I mean just I'm just practicing interviewing, obviously for job interviews. So if you have any suggestions for me, but that you want to say now as opposed to writing them down, I'd be happy to hear them. But otherwise, it was good. Thank you.
I'll fill out some more information, but in general, very well done. The the only like thing, and this is sort of a minor thing, is that
Mm-hmm.
if you are comfortable with other programming languages, they
Mm-hmm.
tend to be a little easier for these types of problems. So C++, like there's a certain um, like it's nice to know like that you have competence in it, and it's definitely like a lower level language than something um, like Python or JavaScript or even Java or something like that.
Mm-hmm.
But these things you kind of get caught up in. There's a lot of sort of details and a lot of like this whole thing here with looping through the array. Like this is like 3 letters in Python. Like it's all super easy. Whereas there's a lot of like remembering of like, wait, it's called size and all this kind of stuff.
Mm-hmm.
So that's really like my only comment, that I have done interviews. Like I used to do a little bit more C++ programming, and I have done interview questions in C++, and I find that I end up spending unneeded mental energy just trying to like get the stupid C++ code to like compile than
Mm-hmm.
I am on focusing on the algorithm and the technique and all that kind of stuff. So yeah, I don't know if you have another language that you're comfortable in that's a little bit sort of higher level, but like that can be something that is helpful for a lot of these like sort of coding challenge style questions.
Yeah,
So
I suppose Verilog is not a good answer.
yeah, yeah.
um, no, so I mean, I've written the most code in C++ and Java.
hmm
Um, I I've done a little bit of Python, but I feel more. I'm a student right now, and part of it is Python's kind of something I've done a little bit on the side, but the courses are I'm taking two different courses that use C++ right now, so it's kind of more in my mind than
Yeah,
other stuff.
that makes sense. That makes sense. Yeah, and you definitely do want to stick with something that you're comfortable with, because the other position you don't want to be in is you saying that you have familiarity and comfort in a certain language, and then you don't remember how to do something basic like how do you get the element out of an array, or how do you like get the value for a key in a map or something like that. And if you don't have that like really down pat, then that also looks a little bit bad too. So yeah, definitely number one, stick to what you're most comfortable with. But yeah, like then I would definitely say like going into it, especially with C++, you're going to want to like definitely have all of your basic like containers down, like the vectors and sets and maps and all that kind of stuff. Just like, and how to insert, how to get at elements, remove them, that kind of thing. Like it's that kind of stuff is just like ridiculously simple in things like Python, and it's a little bit more involved in C++. But if you have it down and it's just like it's in your fingers, like I know exactly how this works, then it should be just fine.
Yeah, I mean, my kind of approach with C++ was I'll going to use this as my interviewing language, and I'm really going to nail all down those little details, and I'll get it to the point where it's really jumping off my fingers like that. That was kind of my thought process.
Nice. Awesome.
Yeah. Thanks for taking the time to interview me. I really appreciate it, and it was a great question.
Yeah, nice. Awesome. Well, hope you enjoy the rest of your evening.
Okay, have a good evening. Bye-bye.
All right, take care.